Welcome to today's paper reading. Today's paper is titled VideoMamba, State Space Model for Efficient Video Understanding. This paper was published on AR14 by Kunchang Li and colleagues from OpenGV Lab and Shanghai AI Laboratory. The abstract introduces VideoMamba, an innovative adaptation of the Mamba model to the video domain. This model addresses the limitations of existing 3D convolution neural networks and video transformers by employing a linear complexity operator, which is essential for efficient long-term video modeling. VideoMamba demonstrates 4 core abilities: scalability in the visual domain without extensive dataset pre-training, sensitivity to recognizing short-term actions with fine-grained motion differences, superiority in long-term video understanding, and compatibility with other modalities, showing robustness in multimodal contexts. These capabilities set a new benchmark for video understanding, providing a scalable and efficient solution. The code and models for VideoMamba are made available for further research and application. The core objective in video understanding is mastering spatiotemporal representations, which presents challenges such as large spatiotemporal redundancy and complex dependencies. Existing solutions like 3D CNNs and video transformers address these challenges to some extent but not comprehensively. VideoMamba introduces a novel approach using a selective state space model, SSM, that balances linear complexity with long-term dynamic modeling, making it suitable for high-resolution long videos. Figure 1 presents a comparison of throughput and memory usage between our VideoMamba and Timesformer T. Timesformer T, which is built on DATT with joint spatiotemporal attention, is used as a baseline for this comparison. All input frames are standardized to a size of 224 by 224. The testing environment includes an NVIDIA A100-80G GPU, running PyTorch 2.1 and CUDA 11.8, with a batch size of 128. The results clearly indicate that VideoMamba offers superior performance in terms of both speed and memory efficiency, making it a more effective solution for both short-term and long-term video understanding tasks. The state space models, SSMs, have demonstrated significant effectiveness in capturing the dynamics and dependencies of language sequences with linear complexity. These models, such as S4 and Mamba, are designed to handle long-range dependencies efficiently. In the domain of video understanding, datasets like UCF-101 and kinetics have been crucial for enhancing action recognition capabilities. The architectural evolution in video understanding has moved from CNNs to more advanced techniques like attention-based models, aiming to balance computational efficiency with performance. Despite advancements, existing models often face high computational costs for long sequences, which our VideoMamba aims to address with its linear complexity operator. State space models, SSMs, are designed to map a 1D sequence through a hidden state using a continuous ordinary differential equation, ODE. This continuous model is then approximated through discretization in practical applications. The VideoMamba framework, on the other hand, projects input videos into non-overlapping spatiotemporal patches using 3D convolution. It employs bidirectional Mamba blocks to process these patches, enhancing spatial awareness and contextual sensitivity. This approach allows for adaptive weight modulation and efficient handling of long videos, making it suitable for complex visual tasks. Figure 2 illustrates the Mamba blocks designed for both 1D and 2D sequences. The figure simplifies the representation by omitting the initial normalization and the final residual connections. This visualization highlights the core structure of the Mamba blocks, which are crucial for processing sequences in different dimensions efficiently. Figure 3 presents the framework of VideoMamba, which adheres to the architecture of vanilla VIT and incorporates the bidirectional Mamba block for 3D video sequences. The framework begins with 3D convolution to project input videos into non-overlapping spatiotemporal patches. It includes a learnable classification token and position embeddings to retain spatiotemporal information. The bidirectional Mamba block is adapted to enhance the model's capacity for 3D video understanding. Figure 4 illustrates the different scan methods used in the VideoMamba framework. The methods include: A. Spatial first, where spatial tokens are organized by location and then stacked frame by frame. B. Temporal first, where temporal tokens are arranged based on the frame and then stacked along the spatial dimension. And C. Spatio-temporal, a hybrid approach that combines both spatial first and temporal first methods, with increased computational costs. The figure highlights that the spatial first bidirectional scan is the most effective and simple, leveraging the linear complexity of Mamba to efficiently handle long videos of high resolution. Figure 5 illustrates various masking strategies designed for VideoMamba, which is optimized for handling long video tasks. The row masking strategy is particularly effective due to the 1D convolution preceding the SSM in VideoMamba's architecture. This strategy enhances performance by maintaining continuity among tokens. The figure distinguishes between two types of row masking, clip row and frame row. Clip row masking involves masking entire video clips, while frame row masking applies to each frame individually. These strategies are crucial for improving the temporal sensitivity and adaptability of VideoMamba, especially when dealing with text modalities. Figure 6 presents the results of ablation studies focusing on the effects of self-distillation and early stopping techniques within the context of VideoMamba's model training. These studies are crucial for understanding how these methods influence the model's performance and efficiency. Notably, VideoMamba's architecture, which differs from traditional transformer models by employing SSM, plays a significant role in the alignment process, particularly in how final outputs are handled. The figure also highlights the importance of the masking strategy, which is integral to the model's ability to process and understand video data effectively. Table 3 presents a comparison of VideoMamba with state-of-the-art models on the scene-related kinetics 400 dataset. The table highlights that VideoMamba, based on the SSM architecture, significantly outperforms other models, particularly the attention-based ViViTL, by achieving a plus 2.0% improvement on kinetics 400 and a plus 3.0% increase on the temporally related SDH dataset. This performance underscores the effectiveness of the SSM-based approach in handling video tasks, demonstrating its superiority over purely attention-based methods. The table also notes that while masked modeling is applicable to Mamba, inconsistent architectures can lead to inferior alignment results. Table 1 presents the different sizes of VideoMamba models, specifically detailing the tiny, small, and middle models. Each model size is characterized by its depth, dimension, and the number of parameters, with the tiny model having 7 million parameters, the small model with 26 million, and the middle model at 74 million. Notably, the base model, which was initially considered, was ultimately excluded from the lineup due to observed suboptimal performance during experiments. This table serves as a critical reference for understanding the scalability and performance trade-offs in the VideoMamba architecture. The experiments were conducted on several datasets including ImageNet 1K, Kinetics 400, and something v2. The training strategies employed included the use of the Atom W optimizer with a cosine learning rate schedule and adjustments to the stochastic depth ratio. Performance was evaluated based on top 1 and top 5 accuracy, as well as the efficiency in terms of the number of parameters used. Figure 7 presents the results of ablation studies focusing on the scan type, frame count, and resolution of models fine-tuned from VideoMamba pre-trained on ImageNet. The study reveals that the spatial first scan type is the most effective, outperforming other methods. Contrary to expectations, higher resolution does not uniformly lead to better performance. However, increasing the number of frames consistently enhances the performance of the models. These findings provide valuable insights into the optimal configurations for video understanding models. Table 2 presents a comprehensive comparison of VideoMamba with other state-of-the-art models on the ImageNet 1K dataset. Notably, VideoMamba achieves superior performance, demonstrating a plus 0.8% improvement over CONVNXTB and a plus 2.0% increase compared to DayTB, all while utilizing fewer parameters. This efficiency is further highlighted by the model's ability to maintain competitive performance against non-isotropic backbones that leverage hierarchical features. By increasing the resolution, VideoMamba reaches a top 1 accuracy of 84% with only 74 parameters, underscoring its effectiveness and scalability in processing long sequences. These results extend to video tasks, emphasizing VideoMamba's robust performance and scalability. Table 4 presents a comparison of VideoMamba with state-of-the-art methods on the temporal-related SDH-v2 dataset. The table highlights that VideoMamba achieves significant improvements over ViveITL, outperforming it by plus 2.0% and plus 3.0% on the Kinetics 400, K400, and something V2, SDH-v2 datasets, respectively. This performance is achieved with reduced computational demands and less pre-training data. Additionally, VideoMamba's results are on par with the current state-of-the-art uniformer, which combines convolution and attention in a non-isotropic structure. In the self-supervised learning domain, VideoMamba's performance under masked pre-training surpasses that of VideoMamba, known for its fine-grained action recognition capabilities. This underscores the potential of the purely SSM-based VideoMamba model in efficiently and effectively understanding short-term videos, making it suitable for both supervised and self-supervised learning paradigms. Table 5 presents the results of ablation studies focused on masked pre-training techniques. The study uses ClipVTB as a teacher model to distill knowledge into VideoMamba over 200 epochs. Key findings include the superiority of row masking over random and tube masking methods, likely due to its compatibility with 1D convolutions and higher degree of randomness. Additionally, attention masking is highlighted as the most efficient, preserving adjacent meaningful content. The study also identifies an optimal masking ratio of 80%, which, combined with stronger regularization, significantly benefits VideoMamba during masked pre-training. Table 6 presents a comprehensive comparison of the state-of-the-art methods on the breakfast and coin datasets. The table highlights the distinction between end-to-end, E2E, methods, which do not rely on exhaustive feature extraction, and those that do. It also identifies the backbones used, such as VideoMamba T, VideoMamba S, and VideoMamba M, with a special marker indicating those that underwent masked pre-training. The performance metrics on these datasets are detailed, providing a clear view of the advancements and current capabilities in video understanding tasks. Table 7 provides a comparison of state-of-the-art methods on the LVE dataset, focusing on end-to-end approaches that do not exhaustively extract features. The table highlights key abbreviations such as REL, for relation, DIR, for director, and WTR, for writer. The comparison metrics include content, metadata, and user, which are essential for evaluating the performance of these methods in relation to the LVE dataset. Table 8 presents the zero-shot text-to-video retrieval performance of various models on 5 prominent benchmarks: MSRVTT, DDMO, ActivityNet, LSMDC, and MSVD. The table highlights that under the same pre-training corpus and similar training strategies, VideoMamba achieves superior zero-shot video retrieval performances compared to UMT based on VIT. This underscores Mamba's comparable efficiency and scalability to VIT in handling multimodal video tasks. Notably, for datasets featuring longer video lengths such as ActivityNet and DDMO, and more complex scenarios like LSMDC, VideoMamba demonstrates a significant improvement. This showcases Mamba's aptitude for the demands of cross-modality alignment even in challenging multimodal contexts. In conclusion, the paper introduces VideoMamba, a model based on SSM that excels in efficient video understanding. The experiments show its scalability in the visual domain, its sensitivity for recognizing short-term actions, and its superiority in comprehending long-term videos. Additionally, VideoMamba demonstrates compatibility with other modalities. Looking ahead, the authors plan to further validate its scalability, incorporate additional modalities such as audio, and integrate it with large language models for more comprehensive hour-level video understanding. Thank you for watching.